all the nutrients are fascinating, but by far nitrogen is, to me, the most interesting nutrient that we deal with on our farms. And the nutrient cycle itself is complex, dynamic, and 100% driven by soil biology, which makes it very unique because none of the other nutrients are like that. The air that we're breathing right now is 78% nitrogen gas. There's a lot of nitrogen in the air, but the plants themselves cannot pull nitrogen out of the air and utilize it. So there's tons of nitrogen out there, and it's just kind of funny that it's the most limiting nutrient for our crops because they cannot access the nitrogen in the air. They can actually only take up two forms of nitrogen, and you've probably heard those forms before, ammonium and nitrate. They cannot take up N2 gas. Now there's a good reason for that. Nitrogen gas has a triple bond, so it's N, if you've ever taken chemistry, with three little lines, N. And that triple bond is very, 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 very difficult to break. And there's really only two ways to break it. And the first way to break that bond is through microbial activity. So something that we cannot even see with our naked eye can actually break that triple bond by taking nitrogen out of the air, and they can utilize it in their microbe bodies, and then they can make that available to plants. Okay? Plants can't do it, we can't do it, but these little dinky microbes can. The other way that nitrogen becomes available to the crop, so there's only two ways possible for nitrogen to become available to plants, and then ultimately to us. Microbes is the first way, and the second way is through this process called the Haber-Bosch process, which is a man-made process to break the triple bond of nitrogen gas and convert it into ammonia gas. This is the green revolution, right? When we were able to move from just relying on the microbes to produce nitrogen for our crops and protein for us, to being able to make this in a factory somewhere, to do the same process. And the Haber-Bosch process, I don't know, I should know the date of that. I mean, it was quite some time ago. Again, revolutionized agriculture. The interesting, absolutely just fascinating aspect of this is the amount of energy that it takes to break that triple bond is immense. It's interesting to think that prior to this process, the only way to get nitrogen, protein, for us and plants was from microbes doing that action. And now, you know, man was able to take a lot of energy to break these triple bonds and make it into ammonia gas. And I think they actually did this for warfare, not for not for agriculture, but the byproduct, you know, of those efforts, you know, bombs and things like that, was that we were able to get fertilizer, commercial fertilizer. Now, we all know that the price of nitrogen continues, you know, to go up, and the price of nitrogen is very closely linked to the price of energy because it takes so much energy to make synthetic nitrogen that as soon as natural gas prices go up or any kind of energy prices, the price of nitrogen skyrockets as well, and that's why. So there's, you know, a take-home message here, which is you can make your own nitrogen. You can do it, well, you can't do it, but you can work with the microbes on your farm to make nitrogen. And it is the only nutrient that you can actually produce on your own. And that is a pretty powerful tool that you have that's usually highly underutilized. But with the increasing cost of nitrogen fertilizers, people are looking more towards working with the microbes to do the job for them. And it makes sense. So again, plant available nitrogen is in the ammonium ion form or the nitrate form. Plants prefer to take up nitrate because once they take up ammonium, they actually have to expend a large amount of energy to break the hydrogens from the nitrogen. And all the hydrogens, especially if they take up a lot of ammonium, can actually end up being toxic to the plants themselves. So they prefer this form of nitrogen over this one. So this is the nitrogen cycle, and you can see it's a little bit more complicated than the old phosphorus cycle. You know, it comes from rocks or manure, and that's pretty much it. Nitrogen has a very complex, biologically driven cycle. So how does nitrogen get into the ground in the first place? Again, you have bacteria that can pull nitrogen gas out of the air and fix it for themselves, and then as they actually break down, it can be released to plants. So that's one way that it happens. Apparently, lightning fixes nitrogen as well, and we don't take lightning credits in Vermont, but they do in California. I think they get like 14 pounds of nitrogen per acre credit for lightning. And then we also get nitrogen for our crops by applying fertilizers that are developed through this Haber-Bosch process, and then also through adding organic materials such as crop residues or cow manure. The organic materials, the organic matter, is carbon attached to nitrogen, and we call that organic nitrogen. That nitrogen cannot be utilized by your crops. They can't, take their roots and slither over to a piece of cow manure and eat the nitrogen off of it. It doesn't work like that. The nitrogen has to be released from the manure. Okay, so this nitrogen carbon bond needs to be broken before that becomes available to your crops. The way this becomes broken is through microbial action. So there's hopefully a plethora of microbes in your soil that can break down the organic matter, and part of the breakdown process generally results in waste products from the microbes that contains plant available nitrogen. This process is called mineralization. Nitrogen becomes mineralized. So it's stuck to carbon, the microbes chew on it, and then part of their byproduct is ammonium that then can be some of it can be utilized by your crops, but then some of the ammonium or most of the ammonium in your soil is subject to further microbial action. So the ammonium in your soil can go through a two-step process to be made into nitrates, and that's the form that your plants like. In order for that to happen, there are two specific bacteria, one that does this conversion and one that does the second conversion. Only two bacteria. There's not a fungi that hops in there anywhere. It's two bacteria, Nitrus monas and Nitrobacter. So in order to have the conversion of ammonium to nitrates, you need to have these two bacteria. If you don't have those two bacteria, you got some problems. You have really poor nitrogen use efficiency generally. The next thing is that you have nitrates. And we learned that your soil hopefully has negative charge. Nitrates have a negative charge. So they're not held on to your soil at all, and they're highly prone to leaching. The other thing that can happen to nitrates in your soil is that they can go through a process called denitrification, which is also bacterially driven, and it takes these nitrates and converts them to nitrogen gases that then get released back into the air. These nitrogen gases in particular, N2X or N2Os, are greenhouse gases. Those are the culprits behind global warming. Where we see denitrification, and we see it quite often, is on heavy clay soils. Because the way denitrification happens is that it only happens in the absence of oxygen. So when you have heavy clay soils that become saturated with water or severely compacted, then you generally move to conditions that are low oxygen, and you sort of favor the bacteria that take those nitrates and convert them into gases. So when we see nitrogen loss in the spring, it's likely that the nitrogen there was lost through denitrification. And you can lose substantial amounts of nitrogen fertilizer through that process, 60% sometimes. So it is a significant loss pathway on heavy soils. And then on other farms where we see yellow corn after major rainstorms, they've generally lost nitrates through leaching, not through denitrification. So again, once you're in the nitrate forms, that's when you have the most kind of plant consumption, because that's really what they like to take up. Okay, so that's the nitrogen cycle. So mineralization is organic nitrogen that is converted to a plant-available form of ammonium by the action of soil microbes. Organic nitrogen comes from the manure you added, the crop residue, the plant roots that have sloughed off, the dead bugs, the mold that died. I mean, it's in the organic form, attached to carbon. Microbes break it down, becomes plant available. In order for this process to happen, generally the soil temperature needs to be above 50 degrees, which is often also why we see a lot of yellow corn in the spring when it's planted very early and the soil temperatures are still cold. Because you may have nitrogen there, you may have just added a lot of manure, but the soil temperatures aren't warm enough for the microbes to get kicking to make the nitrogen available to your crops. So hence, they turn yellow. The other really important factor here is that soil microbes have requirements too. They are a living organism, just like the livestock that you keep on your farm, and you should treat them as such, which means that they need plenty of air, they also need moisture, and they need a nice home to live in. So if you don't create the right environment for your microbes, then they won't be there for you to sort of carry out this process. The opposite action of mineralization is immobilization. And we also see this happen on farms quite often. If you have horses that have sawdust, a lot of sawdust bedding, or calves on bedded packs with sawdust, or you have a bedded pack with a lot of straw. In those cases, you have organic matter that has far more carbon than nitrogen. So there's nitrogen stuck to the carbon, but not very much. Okay, there's a lot more carbon in straw than there is nitrogen, and even though the animals have kind of defecated on it, the amount of carbon there still far exceeds the nitrogen. We call this the C to N ratio, carbon to nitrogen ratio. And so if the carbon to nitrogen ratio is really high, you know, like 20 to 1 or 25 to 1, then you see the opposite. So the microbes still try to break down the organic matter because they're just living. That's what they do. It's not like they're doing it for you. They have no pressure to work for you. They're doing it to stay alive. So they're always going to try to eat that organic matter. And they need nitrogen too. They're trying to build proteins in their bodies as well. And so they actually will take nitrogen out of the soil and use it to break down that organic material if there's not enough on the organic material. In that case, any plant available nitrogen that was just free in your soil gets easily taken up by the microbes to break down the organic matter. And then what happens to your crops that are trying to grow? They're without nitrogen. So if you've ever kind of spread all that bedded pack somewhere in a spot, or you had a manure stack with a lot of bedding or something, and all of a sudden that patch, that's all yellow corn right there, or grass, that's why, because the nitrogen is tied up and not available to the crop. It becomes available over time, but it will, in the short term, immobilize it. So mineralization, immobilization, and now we're talking about nitrification again. So once we have ammonium in the plant available form, there are the two bacteria that I talked about, Nitrus monas and Nitrobacter, just bacteria, that convert ammonium to nitrates. You know, there's not that many processes in the soil where there are very specific microbes that do that work. Usually there's a lot of overlap in the microbe world. But this is a very specific job that these two individual microbes have. And so without them, this process does not happen. And I emphasize that because you want to create an environment where that process is really moving along. So in order for these microbes or the bacteria to really like their living scenario, you need to have warm temperatures. They really like high pHs, not too high, sort of 6 range. And then they need air, moisture, and a nice home. They don't want to be in heavy compacted soils that are waterlogged with nothing to chew on. So it's really important to create a soil environment that is conducive for the little animals that live in your soil. Volatilization is also a part of the nitrogen cycle that we deal with in agriculture, and that is the loss of ammonium nitrogen to ammonia gas that gets lost into the atmosphere. This happens in the presence of oxygen on the soil surface. So we only really see volatilization when you apply ammonium to the surface of the soil, and there's plenty of moisture and plenty of heat to convert that ammonium to ammonia gas. And so, conditions where we see a lot of volatilization are in the hot heat of the summer, where we've gotten a nice rainstorm, and the next day it's 95 degrees, and you can actually kind of see steam rolling off the ground. If you just applied manure, the ammonium nitrogen in the manure will volatilize. Pretty common on hay fields that are spread with manure in the summer. There's significant loss of ammonium nitrogen from those kind of fields. Denitrification, again, is the conversion of ammonium nitrogen to nitrate and then on to these nitrogen gases, especially this one, which is really a greenhouse gas that people are trying to limit in agriculture. The loss pathways I talked about are really important from an environmental perspective, but also from an economic perspective. You don't want to lose 60% of your nitrogen that you just applied to denitrification, and the environment doesn't want to see it either. So, it kind of is a win-win for us to have you minimize these loss pathways. It's really important for us to manage nitrogen and other nutrient losses as well, because I don't know how you economically, you don't really want to be losing all that. We talked briefly about the microbes that can actually take the nitrogen gas out of the air and make it into a plant available form. And I thought I would just talk about that a little bit, because you really are in a unique situation to have a little more control over nitrogen prices than you probably ever thought you did. Prior to 1945, almost all of the protein that we ate or purchased in the store actually came from this microbial process, and now today it's less than 5%. Pretty much all the protein and food that we eat comes from the Haber-Bosch process. So things have really changed in how we farm, and not to say that that's bad at all, because we've definitely seen major increases in productivity and food production and all those things. Let's not forget about this and the potential this has for us as farmers to just kind of make more of our own. So the process, in case you're not familiar with it or didn't know the details of it, is that this bacteria, in particular for alfalfa and clovers, the bacteria's name is Rhizobium, but there's other bacteria that have specific relationships with other legume plants. So soybeans has its own, black beans has its own strain. But the one that we're most concerned with for the folks in this room is Rhizobium. So when you inoculate your clover seed or your alfalfa seed, that's what you're covering it with. You actually are covering it with the Rhizobium bacteria so that it's there when the plant begins to grow. Now, most of our soils, have a history of clover or, history of some kind of legume. So there's probably Rhizobium in the soil somewhere, and it would nodulate. It goes a lot faster when the bacteria is right there. You coat the seed with the Rhizobium, you plant the seed, and then the seed begins to grow, and the little rootlets come out of the plant, and it's at that point that the Rhizobium sees the rootlets, and they fall in love. They do. So they form what we call a symbiotic relationship with each other, and the Rhizobium or the bacteria actually live in these tiny little nodules and form around the plant roots. So the bacteria itself can get the nitrogen out of the air, and they convert it into a form that the legume can use. And then in return, the bacteria receives energy from the crop, or carbon. And that's the symbiotic part. The plant gets nitrogen, and the bacteria gets energy. And that's how they survive. How nitrogen becomes further available to your plants, so if you have grasses growing in those fields, or you're going to grow corn, etc., when these plants are growing, the roots slough off, some of the nodules die and new ones form, and the nitrogen embodied in that becomes available to the crop. If you plow down a crop of legumes or alfalfa, then all the nitrogen that's embodied in these nodules and in the plant biomass itself becomes available to the subsequent crop. So if you actually fertilize your legumes, the alfalfa becomes lazy, and I think you probably read about that or heard about that somewhere, or the legumes become lazy. because they don't want to give up anything if they don't have to. So you kind of have to make them work for it, and not, over-fertilizing, over-manuring your alfalfa or clover fields will lead to a lack of production of nitrogen by the rhizobium. So anyway, that's why we tell you to stay off those fields. So there's other really fascinating relationships that are occurring between plants in your fields. It's something I think about that's increasingly important for a lot of reasons. It's always been important, but we talk about it more today than ever, is just this concept of diversity in your fields, and especially in your perennial forages where you have the ability to have more diverse stands. There's, benefits to just having grass in a field, and maybe benefits to just having legumes, but there's even more benefits to having a strong mixture of lots of different kinds of species of plants. From their rooting types to the relationships they have with each other, there's a lot of benefits. To the microbes that surround this plant versus the microbes that surround that plant actually being very different. Things that we're just beginning to learn and don't know enough about, really, to say, well, if you grew oats next to wheat, and this is an article that just came out a couple years ago in Science. If you grow oats and then you grow wheat, you get this some fungal population in the wheat that will help make more nitrogen available in the subsequent corn crop. I mean, just these amazing shifts in microbial life from even switching from oats to wheat. Just this fascinating world down here that we really know not a whole heck of a lot about. So what I always like to tell people is, build it and they will come. Make a nice place for the microbes, give them lots of different food to chew on and a diversity of plants, and they will come and they will perform these magical things. That's not a term you use in science, but things are going on down there, and we can't explain all of it, and we don't know all the microbes that are responsible, but it does help. And one of the interesting things that people have researched over the last few years is that this connection between the grasses and the legumes, they actually connect by hyphae highways. So there's these microbes in the soil, these fungi called mycorrhizae, that actually form these bridges between the grass and the legumes. And mycorrhizae are known for being able to pull out phosphorus from your soils and make it available to the plants. And so now there's this whole, kind of body of research that's focused on the transfer of nutrients between grasses and legumes along the hyphae highways. So I can't say this is happening in your soil, but I do know if you create the right environment, these things are happening, and they will benefit your crops and the environment as well.